And I'll take it away by first thanking the organizers for inviting me to this program and giving me the opportunity to visit ICTS, which has been an amazing experience. And my talk is going to be a continuation of what Raghav was presenting. As you see, we have a lot of material. And what I'm going to do is first briefly review the Lattice setup that Simon has discussed in several lectures over the past few days, and Raghav just presented in some detail. I'll go through that very quickly. And if I keep up the pace, hopefully we'll have time to get through three sets of results where sort of the unifying theme of each of these works is going to be first trying to reproduce some known results from analytic analyses in regimes where those analytic techniques are reliable, in particular the perturbative regime, and in at least one case, a holographic regime. And then the longer term goal of this program is to use lattice calculations to move beyond those regimes to new domains inaccessible to the currently known analytic techniques. So picking up on what Raghav was presenting about lower dimensions, I will complete the picture of what we've worked on by looking at the maximally supersymmetric theory, dimensionally reduced to 2 dimensions. This is work that came out in the fall in collaboration with Simon, Raghav, and Toby Wiseman. And then I'll present some ongoing work with preliminary results back up in 4 dimensions and at 0 temperature, first for the Coulomb coefficient from the static potential for n equal 4 super Yang mills, and then for the anomalous dimension of the Konishi operator in that theory. And probably I won't have too much time to discuss open questions in future directions, for example, the sign problem. Fortunately, some of those discussions have already come up in Simon's lectures. So since Raghav went through this, let me just remind you that we want to use lattice calculations as a non-perturbative means to investigate strongly coupled supersymmetric gauge theories. And this runs into difficulties from the fact that supersymmetry does not play nicely with the lattice discretization of space-time. And in my work, I've taken the approach of preserving some subalgebra of the super Poincare group, even at non-zero lattice spacing, building on these equivalent constructions from topological twisting and orbifolded dimensional deconstruction that has been reviewed some time ago now by Simon, David Kaplan, and Mitat Unsel. In the twisted language, we have these 5 complexified gauge fields containing the usual gauge fields and the 6 scalars, plus a Kähler-Dirac fermion of 1 + 5 + 10 degrees of freedom that correspond to the sites, links, and plaquettes of the lattice, respectively. In order to have 5 links symmetrically spanning a 4-dimensional space-time, we have to work on this A4 star lattice, which is essentially a higher dimensional generalization of the 2-dimensional triangular lattice. And this introduces some complications, most of which I won't have time to discuss and will gloss over. One complication I should mention right now is that the complexification of the gauge fields leads to gauge invariance under a full UN group in the continuum that decomposes somewhat trivially into an SUN theory of interest times a decoupled U1 sector. On the lattice, that's not so clear, and in order to carry out numerical lattice calculations, we have to regulate zero modes and flat directions in both the SUN sector that is present in the physical theory, as well as the U1 sector that is really an artifact of working at non-zero lattice spacing. We introduce, as Raghav mentioned, 2 deformations in order to control each of these sectors. In the SUN sector, we can just put in a simple scalar potential, which is what Raghav discussed. This involves only the bosonic fields and not the fermions, so it obviously breaks supersymmetry, but it does so softly, which means that all of the supersymmetry violating operators that may be generated by quantum effects are guaranteed to vanish as the tunable coefficient mu squared of the scalar potential is taken to 0. And we can test that by measuring violations of Ward identities, basically the action of this twisted scalar supercharge on some operator is non-zero as a result of this soft supersymmetry breaking. And in this left-hand plot here, I'm showing those violations versus this tunable parameter mu squared and getting a nice linear behavior with vanishing and restoration of this supersymmetry in that limit of mu squared going to 0. For the U1 sector, we do something a bit fancier, which essentially amounts to introducing a Phi-Iliopoulos D-term potential as a way to impose this constraint on the plaquette determinant, essentially fixing the determinant of the plaquette to be unity in a way that is consistent with the scalar supersymmetry. And what this does is give us what I've called an improved action here corresponding to the blue points in this right-hand plot. It's the same ward identity violations on the vertical axis now plotted on a log-log scale with the inverse lattice size. So in the continuum limit, we actually fit a power law here to extract order A squared scaling in the discretization artifacts. The red points up here are what I call an unimproved action, where this plaquette determinant constraint was just added as another supersymmetry violating potential term. These points are also going to 0, but with a very small power, much less than 1 in fact. And here the order A squared behavior can be understood by the fact that exact preservation of this scalar supersymmetry would forbid all dimension 5 order A operators. And by just having this SUN scalar potential, it seems that we preserve the supersymmetry well enough that those operators are negligible in practice, and we can observe this nice order A squared scaling. The downside of these two deformations is that they end up producing a relatively complicated lattice action. In particular, there are something like 100 internode data transfers in each application of the fermion operator, the Matvec operation, which is the main computational cost in the numerical calculations. And in order to reduce the barriers to entry to encourage more people to work in this field, we do all of our code development publicly through the GitHub repository that Ragav mentioned. We also have a manual for the code presented a few years ago, which we hope to update this year because there are many more recent developments, including, in particular, this full improved action that are present in the code but not yet presented in that manual. So let me move on and duck back down from 4 dimensions to 2, just by doing the naive dimensional reduction of working with a 4-dimensional lattice that has a single slice in each of 2 of the spatial directions. So this produces then a 2-dimensional 16 supercharge super Yang-Mills theory, where there are 4 potent twisted scalar supercharges preserved by this construction. If we study low temperatures, which on this plot correspond to large R beta, large inverse temperatures, then we can hope to rely on a leading order supergravity description from holography, where the 2-dimensional field theory is described at non-zero but low temperatures by the behavior of certain black hole solutions in supergravity. In particular, when the spatial extent of the 2-dimensional torus that we're considering is large, we expect to have homogeneous black strings, D1 phase in the dual gravity, which then it becomes unstable and transitions to a localized black hole phase, what we call a D0 phase, when the length of the torus in the spatial direction becomes sufficiently small. At high temperatures or small R beta, the fermions pick up large thermal masses and effectively decouple, leading in that limit to a bosonic quantum mechanics, where this transition is believed to correspond to a deconfinement transition, or what we'll call it a spatial deconfinement transition. What that amounts to is that the expectation value of the Wilson line in that spatial direction goes from 0 in a spatially confined phase to a non-zero value corresponding to this gravitational transition. So as I was saying at the start of this talk, we want to ideally reproduce this known behavior from the simplified bosonic quantum mechanics limits at high temperature on the one hand, and the dual supergravity holographic predictions in the other limit, and then smoothly connect those two through non-perturbative lattice calculations. So in principle, this is a straightforward exercise. We generate lots of ensembles, measure the Wilson line in the spatial direction and see a pretty clear transition as we increase the length of the spatial direction of the torus. The procedure that we're taking is to fix the aspect ratio of all of these systems, and then what I've plotted here is the Wilson line expectation value versus the inverse temperature, so the thermal extent of the lattice R beta, which is now, because the aspect ratio is fixed, directly proportional to the size of the spatial cycle on that torus. And as we go from a very small RL, so a small torus, we see a non-zero expectation value for the Polyakov loop, which then transitions to become much smaller, and in particular, we see that as the number of colors in the gauge groups that we're simulating increases from 6 to 9 to 12, there's a steady decrease towards the exactly vanishing Polyakov loop that we expect in the limit of infinite n, which is also an important limit to control corrections to leading order holography. So from this example is at an aspect ratio of alpha equals 4, and we see a transition at roughly R beta above 0.2, corresponding to RL between 0.8 to 0.9, and that is shown by this point here on the same axes as the cartoon on the previous slide. And hopefully the thin dashed lines on this plot are visible. Those correspond to the fixed alpha lines along which we are scanning to pick out these transitions. So this lowest line here is alpha of 4 with this transition around RL of 0.8. And then as we go to lower and lower alpha, so alpha of 2, 1, and even a half, where the thermal extent of the torus is longer than the spatial extent, we move to we probe the transitions at lower and lower temperatures, which unfortunately necessarily leads to, as you can see, larger and larger uncertainties in the transition results. But at least modulo those uncertainties, we are reasonably consistent with the holographic prediction at reasonably large RL, at least somewhat larger than 1, and at smaller RL below 1, we do end up bang on the simpler bosonic quantum mechanics limit. So we see at least rough consistency with both of those expected asymptotic behaviors. We can also do a little bit more with this system before I move on to 4 dimensions, and that is to look at the bosonic action of the field theory, which is related by holography to the internal energies of the dual black holes. So from holography, there are slightly different predictions for the behavior of this observable in the D1 phase, where we have a homogeneous black string wrapping around the spatial direction, and the D0 phase, where we have a localized black hole. Both the prefactors and the powers of the temperature dependence of the bosonic action are predicted by the leading order supergravity in both of these phases. Here I'm just showing the 2 different powers, bosonic action scaling proportional to T cubed in the D1 phase at large spatial radii, and a power of 3.2, the 16.5 that you saw earlier for the D0 phase at small r. And here are our numerical measurements for this quantity, appropriately normalized, compared to that leading order holographic prediction, where we see, again, reasonable rough agreement at sufficiently low temperatures below roughly 0.4 on each of these plots. This is a first look at this system that can be improved in the future by really taking controlled extrapolations both to the limit of infinite n, which the holographic relation relies upon, as well as the infinite volume limit, which corresponds to the continuum limit on a torus of a fixed finite size, corresponding to this temperature given here. But what we're showing on these plots is at least an initial confirmation that those extrapolations appear to be mild. We have in both cases for the D1 phase on the left and D0 phase on the right, a couple of different lattice volumes and a couple of different values of n going up to the 16 color theory. where we see mostly agreement within relatively large error bars, suggesting that as we proceed and make these results more precise in the future, we will be able to get some controlled infinite n continuum limit results in agreement with holographic predictions for sufficiently low temperatures, and then potentially probing corrections to the leading order holography that become important at higher temperatures. And as has been discussed by Masanori, Ansheim, and Androgov already, to get to even lower temperatures on these plots, we need to go to larger values of n in order to control these thermal instabilities that appear at low temperatures. Good, so now let me jump back up into 4 dimensions and start just to show you some results from the lattice formulation that we've already discussed. First, looking at the static potential. Now, the static potential is measuring effectively the energy of corresponding to 2 static fundamental probes at a fixed separation in the system. So what this amounts to is that at some time we create these 2 infinitely heavy probes, separate them to some separation r, and then let them propagate forward and backward in time, so effectively a quark and an antiquark, before annihilating them at some later time. I'm just going through this exercise to explain why this static potential corresponds to investigating these rectangular Wilson loops, as I described here, oriented with one edge in the temporal direction. The Wilson loops in particular decay exponentially in the temporal extent, and they do so with the prefactor of that exponential decay is just the static potential at the corresponding distance r that we're interested in extracting. In order to reduce some of the complications I mentioned from working on this A4 star lattice with a degenerate non-orthogonal set of basis vectors, what we do in all of the results I'm going to show you is apply an old trick, or a classic trick I should call it, from lattice QCD, which is to fix the Coulomb gauge and then replace this Wilson loop by just the product of links along the 2 temporal sides with nothing connecting them at the top and the bottom. This is obviously, this is not a gauge invariant quantity, but by fixing the Coulomb gauge, where we impose a maximization condition on the 3 links that span each time slice on the lattice, we ensure that only gauge singlet information is propagating in time, and that we continue to extract the static potential from the same exponential decay of these Wilson loops. So I'll skip straight to the results for how the static potential looks as a function of R for 2, 3, and 4 color gauge theories. Plotted here all on top of each other since they all look rather similar, and fit to, in this plot, just the simple Coulomb potential of a constant minus a 1 over R term. What we do first, of course, is to fit these data to the full confining static potential that those of you doing QCD in the audience are used to, that also includes a string tension term, 1 over R plus a sigma times R. We see when we do that that the string tension is always consistent with 0, corresponding to a Coulombic potential at all of the couplings we are able to access, which is what we expect from n equal 4 super Yang-Mills, which is in the non-abelian Coulomb phase and should not exhibit a confining static potential. We can then throw out the static potential term, simplify the fit to just the Coulomb potential, and use those fits to extract the Coulomb coefficient, this C, as a function of the coupling. I will mention just in passing that these results are benefiting from another classic trick from lattice QCD, which is to incorporate a tree-level perturbative improvement into the analysis, which has really cleaned up these results a lot, and I'm very happy about it, but I'm going to bite the bullet and give into the clock and skip that detail in order to show you more of the results that we have. First, for, as I said, the Coulomb coefficient as a function of the coupling lambda, where this square root 5 decoration is another complication of the A4 star lattice that I'm glossing over. A constant rescaling factor to relate the lattice coupling to a continuum coupling of n equal 4 super Yang-Mills. Now there are predictions for the coupling dependence of this Coulomb coefficient from both continuum perturbation theory as well as holography. In continuum perturbation theory, it's just a simple power series in lambda. What I've shown here is the next to leading order perturbative prediction, including values up to lambda cubed. In the holographic domain that corresponds to the limit of both infinite number of colors in the gauge theory as well as an infinite 't Hooft coupling, with the restriction that the 't Hooft coupling remain much smaller than the number of colors, this behavior is predicted at leading order to turn into a famous square root dependence. This was one of the first predictions from ADS CFT holography, and Brigov gave you the citation that I've omitted from Maldasena's work back in 98 or 99. What we see in the results so far is no sign of this turnover from a linear plus higher order corrections to this weaker square root dependence in L. We see actually surprisingly good agreement with perturbation theory given the restrictions of the lattice calculations done so far, which are on a single relatively small volume with some larger volume consistency tests, but still a maximum of 16 cubed times 24 lattice volume. Again, for 2, 3, and 4 colors, all ending up pretty much on top of each other. They match quite well with next to leading order perturbation theory, and to some extent, I think that agreement is coincidental, but it's certainly encouraging, and hopefully will be finalized in the near future. So I have, I think, just enough time to present some even more preliminary results for the scaling dimension of the Konishi operator in n equal 4 super Yang-Mills that Madalena talked about 2 days ago on Monday. As she mentioned, this Konishi operator is just the symmetric product of 2 of the scalar fields of n equal 4 super Yang-Mills, essentially the simplest conformal primary operator. And again, there are many analytic predictions for its scaling dimension, 2 plus this non-trivial anomalous dimension as a function of the 't Hooft coupling. Again, from perturbation theory at weak 't Hooft coupling, which is related to the strong 't Hooft coupling limit via S-duality, and then holography in that usual 't Hooft domain of large n and large lambda. And we also heard about some numerical conformal bootstrap constraints on the maximum value of this operator. On the lattice, we have a prescription to extract the scalar fields from the complexified links of this lattice theory and define a lattice interpolating operator, which as a singlet scalar picks up some mixing with the vacuum that we have to subtract, which is always a fun procedure in lattice gauge theory. And what I'm showing on this plot is, again, a log-log plot with the straight lines corresponding to power laws for this Konishi operator, or the correlator constructed from this Konishi operator are the red points, compared to this green power law is the leading order perturbative prediction, again, linear in lambda. The blue points are what I call the Sugra operator, just the 20 prime that we heard about, whose scaling dimension is protected at its engineering value of simply 2. And we can see that the agreement between these Sugra points and the protected power law is not so good, possibly just because it's a few orders of magnitude smaller numerically and needs some more work to resolve these relatively small values. Now, of course, we could try to extract a prediction for the scaling dimension rather than comparing with perturbation theory by directly fitting these points to a power law over some limited range in R. And in order to handle some of the systematics corresponding to that, we're also looking at some other approaches, including finite size scaling and Monte Carlo normalization group analysis. And I've highlighted the MCRG here because I will present that just briefly. I am running out of time, so I will gloss over this. Just to remind you of the MCRG perspective, let me call it, that we have the system described as some point in an infinite dimensional space of couplings that correspond to operators, essentially all of which are irrelevant. And under RG transformations, the system flows in this space of couplings, where the fixed point is defined by no longer flowing, like it says on the tin. The RG flow is fixed at that point, corresponding to these couplings C star. We define a stability matrix as the linearization, linear expansion around such a fixed point. So what happens right around in the vicinity of that fixed point, going from an RG blocking step n-1 to n. From the 70s, there's a prescription to compute the matrix elements of the stability matrix from correlators of the operators of interest, and then diagonalizing that predicts the scaling dimensions of those operators. So the preliminary result for the Konishi we have here are, again, roughly consistent with perturbation theory at these relatively weak couplings, far from the bootstrap bounds that are up there and might be saturated at stronger couplings approaching the S-dual point. And there are both some statistical and systematic uncertainties on these points and additional systematic uncertainties to be handled by looking at the number of RG blockings we can do and the final blocked volume from comparing these different lattice volumes, again, for 2, 3, and 4 colors. There's also a complication that in the twisted construction, the Konishi and Sugra operator actually mix. And we're working on promoting this to a variational analysis that can disentangle this mixing. And I won't say anything about that. I'll just recap by saying that I think we're seeing significant progress on the path toward the goals of these lattice investigations to reproduce perturbative and holographic predictions and then try to explore the non-perturbative domain beyond the regimes where we have robust analytic predictions. And there are many more directions that are being or can be pursued, some of which we have heard about and will hear more about in this program. There are also some other programs coming up later this year that I will take this opportunity to advertise briefly. A numerical holography workshop, a shorter event in May in Edinburgh, and then a more phenomenological workshop looking at QCD-like composite dark matter in ICTS Star Trento in the fall. Thank you.
Questions?
So how much bigger of a lattice do you think you would need to disentangle the finite size from the basically power laws that you want?
So these results here are for a 16 to the 4th lattice, which I see I neglected to mention. And at least for the Konishi, we can get something reasonable from that size lattice. And 16 to the 4th, of course, the size we can get to in practice depends on the number of colors that we have. And 16 to the 4th is pretty challenging for the 4-color gauge theory. And since we can do U4 with 16 to the 4th, that's about the same complexity as U2 with 32 to the 4th. So that's sort of the upper bounds that I could promise in the foreseeable future. And being able to compare this direct power law fit on 16 to the 4th with an improved, a larger volume, 32 to the 4th, where we would have a larger range of R accessible before starting to hit wraparound finite volume effects, would, I think, give us a pretty robust sense in how reliable those power law fits would be. Of course, we can do that for the 2-color case that is sort of maximally far from, say, the holographic regime. And then we would have to take that information about finite size effects from 2-color analyses and attempt to apply it then to 3 and 4 or higher colors where we would be limited to smaller lattice volumes in total. So that's the path forward that I can see.
David, I'm impressed by your nice results on the Monte Carlo randomization group. I'm wondering, you just have 3 lattice sizes. Did you use a particular trick like the Damon method to get these good numbers? These small error bars on the left? Or was it a brute force MRG method?
It's brute force MCRG, and one thing I am doing is improving the analysis by constructing several different interpolating operators for both the Konishi and the Sugra by applying some Ape-like smearing. So we smear some number of times, and that gives, so it's analogous to a glue ball operator. We construct essentially the same operator, but with fields that have been smeared through the Ape constructions, or something analogous to the Ape construction for this system, up to 5 or 10 times. And we stick all of those, both the Konishi and the Sugra, into the stability matrix and diagonalize that whole thing. This can help both stabilize the results when it works, just by extracting some more information from the data that we have. It can also, if we do it wrong, it can destabilize the results. If the operators are too similar, essentially there are degeneracies and the matrix becomes singular. So there are a lot of moving pieces in this analysis to which we have to add even more to handle this complication that I've put up with, or I've mentioned. So that's why I think it's not surprising to be dominated by systematic uncertainties in the end. And to some extent, the uncertainties here look small because I've zoomed out large enough to fit the bootstrap bound in way up there, well above the range we're looking at. So it's a challenging analysis, but I think we are making progress towards getting something solid from it.
So just on this slide, how many operators would have to be included for this complete mixing analysis?
So the same number of operators are going to be included, at least that's our current plan. Then the change comes at the stage of implementing a variational analysis where essentially instead of diagonalizing the stability matrix and identifying the leading eigenvalue as the Konishi operator and the next leading as the Sugra operator, we need to essentially, I should have made a slide on this because it's too complicated for me to discuss just in words, I think. It's going to look a lot like the sort of variational analyses that one does, say, in a glue ball analysis, where really here I'm thinking mainly about the power law fit, actually, and not so much the stability matrix. So instead of, in this plot, we just take the correlator of the Konishi operators, we've defined it on the lattice, and the Sugra operator, we would have to construct the full correlation matrix of Konishi and Sugra operators and diagonalize that in order to extract this power law, which I've started work on and have some preliminary results, but nothing ready to show at this point. So this is the sort of variational analysis that I have in mind and mentioned there.
If there are no further questions.